Hello friends, my name is Divya Srivavi, working as Assistant Professor in the Department of ECE SJBIT. In today's video, I'll be explaining the effect of noise in FM system. So here, this is the block diagram of FM receiver, noisy model of a FM receiver. The noise signal W of t, here it is modeled as a white Gaussian noise where you have a zero mean and power spectral density is equal to N0 by 2. The received FM signal S of t, it has a carrier frequency Fc and transmission bandwidth of Bt, such that a negligible amount of power lies outside the frequency band, that is Fc plus or minus Bt by 2 for all the positive frequency. In case of AM, the band pass filter was used, which is having a mid band frequency Fc and the bandwidth is equal to Bt. Therefore, it passes the FM signal essentially without any distortion. So Bt, it is very small compared with the mid band frequency Fc, so that we may use the narrow band representation of N of t. The filter version of the noise W of t in terms of its in phase and quadrature components will be using. So in FM system, the message information it is transmitted by the variation of the instantaneous frequency of a sinusoidal carrier signal, and its amplitude is maintained constant. Therefore, any variation of the carrier amplitude at the receiver input must result from the noise or any interference. So we'll use a amplitude limiter following the band pass filter in the receiver model here. So it is used to remove any amplitude variations by clipping the modulated wave at the filtered output almost to the zero axis. So the resulting rectangular wave, it is then rounded off by another band pass filter that is an integral part of the limiter. Here in the limiter itself we'll have another band pass filter. Thereby we are suppressing any harmonics of the carrier frequency. Thus the filter output, it is again a sinusoidal wave with an amplitude. It is practically independent of the carrier amplitude at the receiver input. So the discriminator, it consists of two components in this model. One is a slope network, or you can also call it as a differentiator, with a purely imaginary transfer function that varies linearly with frequency. It produces a hybrid modulated wave in which both amplitude and frequency vary in accordance with the message signal. And we have an envelope detector that recovers the amplitude variation and thus it reproduces the message signal. So the slope network in the discriminator and the envelope detector, they are usually implemented as a part of a single physical unit. The post detection filter, labeled as a baseband low pass filter, it has a bandwidth that is just sufficient enough to accommodate the highest frequency component of the message signal. This filter removes the out of band components of the noise at the discriminator output, and thereby it keeps the effects of the output noise to a minimum value. So this is the equation for S of t, that is, since this is a FM signal, modulated wave, AC into cos of 2 pi fct plus 2 pi kf into integral 0 to t m of t into dt. The filter noise at the band pass filter output, it is defined in terms of the in phase and quadrature component. N of t is equal to Ni of t into cos 2 pi f ct minus Nq of t into sin 2 pi f ct. So we may express N of t as R of t into cos 2 pi f ct plus psi of t. How do we get this? Is we need to look into the diagram here. R of t into cos 2 pi of psi 2 pi f ct plus the angle psi of t, where R of t is nothing but Pythagoras theorem. We know that it is Ni square plus Nq of square into the integral square root. And what is the phase psi of t? It is tan inverse of Nq of t by Ni of t. That is tan theta is equal to opposite by adjacent side. So the envelope R of t, it is Rayleigh distributed, and the phase psi, it is uniformly distributed over 2 pi radians. So here in the equation S of t is equal to AC into cos 2 pi f ct plus 2 pi kf into integral 0 to t m of t dt. AC is the carrier signal, carrier amplitude. Fc is the frequency, carrier frequency. Kf is the carrier sensitivity. M of t is the message signal. So in FM there is no need to introduce a scaling factor in the definition of the modulated signal S of t, since it is reasonable to assume that its amplitude AC, it has the same unit as that of the additive noise component N of t. So we will directly proceed with the factor phi is equal to 2 pi kf into integral 0 to t m of tau d tau. This one. So the simplified expression of S of t is equal to S of t is equal to AC into cos of 2 pi f ct plus psi of t. Now the noisy signal at the band pass filter, it is given by x of t is equal to S of t plus N of t. What is S of t? AC into cos of 2 pi f ct plus phi of t. Plus what is R of t? Sorry, N of t. Just now we have derived N of t is equal to R of t into cos of 2 pi f ct plus psi of t. It is informative to represent x of t by means of the phasor diagram. As you can see in the diagram, we have to use the relations how to find sin theta, cos theta, tan theta, and then we have to assume certain things here. So in this diagram we have used a signal term as a reference. The phase angle phi of t of the phase theta of t of the resultant phasor representing x of t. So from the phasor diagram, let this be 0 and we are expressing 2 pi f ct. With the phase angle phi of t, we have a signal with amplitude AC, and we'll assume theta of t is over here, and R of t is with the phase angle psi of t. So what is this angle? This is theta of t minus phi of t. So it representative sides. It is taken with respect to sin theta and cos theta, tan theta formulas. So with the help of the phasor diagram, it is assumed that psi of t is greater than phi of t and AC is very much greater than R of t. So tan of the angle theta of t minus phi of t, it is given by the opposite side, R of t into sin of psi of t minus phi of t divided by the adjacent side. Adjacent side is AC plus what is this angle? This length, it is R of t into cos of psi of t minus phi of t. Since AC is very much greater than R of t, we can write the tan of theta of t minus phi of t is equal to R of t into sin of psi of t minus phi of t divided by, since AC is very much greater than this whole term, we have only AC. So here we also have the assumption that psi of t is greater than phi of t. So tan of theta of t minus phi of t is equal to r of t into sine of greater value minus a very smaller value is greater value. So sine of greater value divided by AC. So transferring tan to RHS and transferring minus phi of t to RHS, we'll have this equation. So we also know that phi of t is equal to 2 pi f kf into integral 0 to t m of t. So v of t is equal to 1 over 2 pi into differentiation of d theta by dt. So now v of t is equal to 1 over 2 pi d by dt of theta of t. What is theta of t? This equation. So here in this equation, in place of phi of t, I am replacing it with this equation. So the final equation will be v of t is equal to 1 over 2 pi into d by dt of 2 pi kf integral 0 to t m of t dt plus r of t into sine psi of t divided by AC. Now we will do the simplification. 1 over 2 pi differentiation of 2 pi kf into integral of something m of t into dt. Integration differentiation is there, gets cancelled out. It is 2 pi kf into m of t plus the differentiation of this term 1 over 2 pi into AC d by dt of r of t sine psi of t. So here 2 pi gets cancelled. It is kf into m of t plus 1 over 2 pi AC into d by dt of, what is r of t into sine psi of t? It is n dt of t. So that is the average power of the message signal. It is given by kf square into m square, that is kf square into p. So we thus see that the carrier signal to noise ratio is high. The discriminator output V of t, it consists of the original message signal, or you can say modulated wave m of t, which is multiplied by a constant kf plus some additive noise nd. So here ns is equal to 1 over 2 pi AC into d by dt of r of t into sine psi of t. I am just replacing r of t sine psi of t by nd of t. So taking the Fourier transform of both sides, will get Sns of f is equal to f square by AC square into Snd of f. So this is the power spectral density of Nd of t. From the phasor diagram, we know that the effect of variation in the phase phi of the narrowband noise appears in combination with the single term phi of t. So we know that the quadrature component nq of t of the filtered noise is r of t into sine psi of t. So we are replacing it with that. This means that the additive noise nd of t appearing at the discriminator output, it is determined effectively by the carrier amplitude AC and the quadrature component nq of t of the narrowband noise n of t. Then we need to find the average power. Average power of noise is obtained by integrating the Sn of f with respect to minus w to plus w, or minus omega to plus omega. Minus w to plus w, f square divided by c square into a naught into df. So integrating that, we will get this equation. SNR output, it is equal to kf square p divided by this equation, 2n naught w cube divided by 3ac square. So the final SNRO is this equation. The average power in the FM wave is AC square by 2. So figure of merit is the ratio of these two equations. Figure of merit of FM is 3 kf square p divided by w square. So we can recall that the frequency deviation delta f, it is proportional to the frequency sensitivity kf of the modulator. Also by the definition, the deviation ratio d, it is equal to the frequency deviation delta f. Deviation is proportional to the delta f, which is divided by the message bandwidth w. In other words, we can also say that deviation ratio d is proportional to kf into p to the power of 1 by 2 divided by w. The figure of merit of a wide band FM system is a quadratic function of the deviation ratio. So in wideband FM, the transmission bandwidth Pt is approximately proportional to the deviation ratio d. So we may state that when carrier to noise ratio is high, an increase in the transmission bandwidth Bt, it provides a corresponding quadratic increase in the output signal to noise ratio, or you can also say figure of merit of FM. The important point to note from this statement is that unlike AM, the use of FM does provide a useful mechanism for the exchange of increased transmission bandwidth for improved noise performance. So when you rearrange these terms, you will get figure of merit is equal to 1.5 times the beta. So here, comparing these things, comparison of AM and FM, we'll assume that the modulation index for both the system, it is adjusted to 1. Hence, as proved earlier, the figure of merit of AM is 0.33, but the figure of merit of FM is 1.5. Moreover, we can increase the value of modulation index beta of FM beyond 1, but in AM it will cause distortion. Therefore, we can say that the noise performance of FM system will always be better than AM system. And then we have a FM threshold effect. Looking into the SNR output equation, it is valid only if the carrier to noise ratio is high. However, practically it is observed that as the input noise increases, the carrier to noise ratio decreases and the FM receiver breaks. So assuming that no signal is present and the carrier wave is unmodulated, the frequency discriminator output, it is given by x of t is equal to AC plus Ni of t into cos 2 pi fct minus Nq of t into sin 2 pi fct. So we have the equations. Individual clicks are heard in the receiver output. It is the indication that the receiver begins to break. So the capture effect is FM system will have a minimal effect of unwanted signals. Also applies to the interference produced by another frequency modulated signal whose frequency content is very close to the carrier frequency of the desired FM wave. However, interference suppression in an FM receiver works well only when the interference is weaker than the desired FM input. When the interference is the stronger one of the two, the receiver locks onto the stronger signal and thereby suppresses the desired FM input. When they are of nearly equal strength, the receiver fluctuates back and forth between them. This phenomena we call it as a capture effect, which describes another distinctive characteristics of the modulation, frequency modulation. So this is all about the FM system, how noise is going to affect the system. and what is the figure of merit, what is the capture effect, what is the threshold effect. Thank you.